Now we need two things before we can continue to the third problem. One is that the masses of these elementary particles and the atomic particles are very small, right? And we prefer to use a different unit. And we use the mega electron volt over c squared. Well, c is the light speed, by the way. And the electron volt is basically the energy that an electron gets if you accelerate it over 1 volt potential difference. So that's a very tiny amount of joules, but of course, with these particles, that's a lot of energy anyway. So we know Einstein, of course, E equals mc squared, right? So you put in the mass of the electron, light speed squared, then comes this energy, right? And that's, with this translation basically, that leads to roughly half a mega electron volt in energy. So if you divide it by c squared, then basically you have the mass. So that means the mass of the electron, we say, is roughly 0.5 mega electron volts over c squared. Well, usually people just say the mass is 0.5 mega electron volt. Of course, we mean over c squared, but that's roughly the same unit. So these are the units we are using, and that means for the three particles that we know, the electron, the proton, and the neutron, these are the actual masses in kilograms. In mega electron volt over c squared, it's roughly 0.5, and these are roughly the same, almost 1,000, right? So many times more, almost 2,000 times as much. That's one thing. The other thing is that if we look at forces, then previously forces were described as force fields. Basically, like gravity, in every point in this room, you can detect gravity pointing downwards to the center of the Earth or go outside. Also with electromagnetic fields, you can basically indicate for every position in the room what the field is, what direction, what strength, and that's basically a field. Einstein said that, well, with electromagnetism and light-related phenomena, you can also describe it with particles. Basically, particles, well, he called them light quanta, little bits of light, and later they called them photons. So basically they are massless, but they contain energy. So a sort of particle. So a particle description also works. And that means that repulsion between electrons now can be understood as the interaction between two electrons where they swap a particle. Basically, if two people are standing away from each other, are getting closer by, suppose you're rolling towards each other on roller skates, and then I have a bowling ball and I throw the bowling ball to the other one. Then I will move backwards, and the one who catches the bowling ball will also move backwards. So that's repelling, basically, the interaction via the exchange of particles, right? So you can understand that forces can also be described as the exchange of particles. So here we see the exchange of a photon between electrons, and then the electrons move apart again. Now there's also, of course, attractive force. It's slightly difficult, more difficult to describe. You can't describe with bowling balls, but basically you can also attract by exchanging particles. So that's the particle way of looking at forces. Now the third problem was, of course, how do these nucleons stay together in the atomic nucleus, especially the protons that repel. Now Yukawa said, well, perhaps there's a stronger force, which was actually called the strong interaction or the strong force later on. That's stronger than the electrostatic repulsion that puts them together. And he said, well, there must be a particle that basically is exchanged between these protons and neutrons, and that particle has to have a mass somewhere in between the electron and the proton mass. So we call it, he called it a meson, something with an intermediate average mass, from the Greek word. And he said, well, it should be roughly around 100 mega electron volt, so very roughly in between. Now a couple of years later, 2 years later, Anderson, that we saw before, did an experiment, and he found in a bubble chamber that looks like this roughly. You see all these tracks, these are all particles leaving these tracks. He did an experiment and he found a negative particle with this mass, so very close to Yukawa's meson, except that this particle that he found wasn't the particle they were looking for, because it didn't interact well, the strong interaction, didn't take part in the strong interaction. So it couldn't explain how the particles stuck together. So basically when they found this, another physicist said, well, who ordered this? As if you've ordered pizza and then you all have your pizza and then there's the pizza with artichokes, which nobody likes, and who ordered that, right? Something like that. So we have these particles, we were looking for this interaction particle, and out comes another particle that we didn't look for, we don't need, and nobody knows what to do with. Luckily, 10 years, 11 years later, Paul did experiments with photoemulsion, so not bubble chambers, but actual well, layers of sensitive liquid. And he found tracks. You can see a pion track here, and then it decays into this muon here. It travels 60 centimeters, and then it decays into an electron here. Of course, that there's an angle here means that there must be another particle shooting off in the other direction, right? Apparently a neutral particle, because these are charged particles. A couple of years later, they found the neutral pion, also always more difficult, but these were Yukawa's interaction particles, basically. Now we have the masses here, slightly higher than the muon, and Yukawa chose this letter because of the similarity to the symbol for intermediate in simplified Japanese, the kanji character. It looks like a pi, right? So that's why they're called pions. So basically, we have all the particles describe matter, even the interaction between particles. We can explain the velocity differences between electrons. So basically, we have the anti-electron, the positron. So yeah, sort of, all right. Can we celebrate that now? Well, no.